terminal or a non-terminal node in this tree. So it's either a leaf or a non-leaf node in this tree. So to go back to the homework example, we had that table over there. So I'll just draw it again here for argument. So A, B, C, D, and it was 1, 0, 1, 1, 0, 1, 0, 1. So let's draw the tree for this. So we see that A is 1, so we'll just write A over here. So A is 1. And we can mark it this way, and using the high-tech approach, I'll put a green circle around that. That's A. B is 0, 1, so that's B, and I'll put a circle around that as well. C is 1, 0, so that's C. I'll put a circle around this guy here. And D is 1, 0, 1, 0, 1, it's over here. That's D. And we have this over here. So that's the tree representation of this code book. So as you can see, if I have any code book where the codes are over the binary strings, I can always draw a tree for it. Okay, that's a straightforward thing to do. And so this allows us to do some couple of clever observations. The first observation is, what is an instantaneous code? Okay, what's an instantaneous code? Well, consider C over here. So I got A and then I got C. The thing is that A is a substring of C. Okay, A is a substring of C and C is a substring of D. In fact, both A and C are substrings of D. So we get right away the fact that if a particular green circle is on the path to any other green circle, it can't be instantaneous, right? Because I have to go further to figure out whether it was actually C or not. So to be more precise, let's say I get 1, 1, then I know that must have been A, right, over here. But if I see 1, 0, it could be either it has to be a C. So it's not instantaneous because of that. But if it's instantaneous, the minute I get to a green circle, so let's say I didn't have these circles over here. So let me just draw another tree over here. And it turns out that this is where all the green circles were. Okay, there was one here and there was one here. Okay, no green circle is on the path to any other green circle. And a little thought should convince you that this makes the code instantaneous. Okay, we have unambiguously know when we see a green circle, there's nothing below us, right? There's nothing below us, so we don't have to worry about having to look into the future to figure out what the code word was. Okay, so this is instantaneous and this is not. Okay, so the rule becomes look for green circles, which are the code words, and just see if anything in the descendant has a green circle or not. If the descendants don't have green circles, you're done, right? Okay, and that's the rule for instantaneous codes. Any questions about that? Yeah.
I have a comment about the way you draw it.
Okay.
We can have two ways, two definitions for the first is that we draw every branch that we consider the height, and we draw every branch.
Uh-huh.
The other definition is that we draw the branch that are needed, that we are having classes.
Right.
In your tree, I don't have, my own definition is the latter. I'm wondering what's your definition about drawing which, how far you should extend drawing here?
I'll answer that in a minute. Okay, so the question is, how big a tree do you need to draw? I'll come to that in just 1 minute. If you just give me 1 minute, that's the next thing I'm going to draw. Okay. So, but the question I'm asking is, you understand that we can't have a term, we can't have a code word on the path to the code word if it's instantaneous, right? That's the point to get across. Okay, this rule then allows us to compute the inequality called the Kraft inequality, which is sort of a famous inequality. And let me just draw that. So we assume that code words. Then length of code words is less than or equal to L. Okay, L is some maximum code word length. Okay. What we'll do is we'll construct the full binary tree of height L. So that's going to answer your question. So let's say L, for the sake of argument, is 3, or let's say make it 4. Okay, I'm going to construct the full binary tree of height 4. So I'm going to have 16 nodes. Okay, so maybe I should have used 3 instead. Well, it's okay. I have a big whiteboard, blackboard there. So that's the full binary tree of height 4. Okay. Now I want to choose an instantaneous code here. Okay. If it's instantaneous code, I know something, which is that if I put a green circle over here, there are no green circles over here. All right. If I put a green circle here, that's good. I can put a green circle here, and then I'm going to put a green circle over there. There can't be anything over here, and then there's nothing on that whole path. Okay. So if I look at all the terminal nodes, the leaf nodes, I'm going to classify them into 3 sets. The 3 sets are those that are terminal nodes, like these guys here. I'll put a rectangle like that. So those are terminal nodes, which are leaf nodes that are also code words, right? Obviously, there's some that are like that. There are others which are going to be descendants of code words, but are themselves not code words, which are these guys over here. And there are going to be some which are neither descendants of code words nor code words themselves, which are these circled ones over here. Okay? And so it should be clear that all leaf nodes must fall into one of these 3 categories. Either they're code words, or they're descendants of code words, or they're neither descendants of code words nor code words themselves. And if L is given to us, we know that this is going to be 2 to the L. We know there are 2 to the L such nodes, in this case 2 to the 4, right? Okay, so given this, we can write down, we also know there's a non-intersecting sets. Okay, we can't be both. You can't be both a descendant of code word and not a descendant of the code word, right? So these are non-intersecting sets, and there's 2 to the L of them. So we have a very simple counting argument, and which allows us to write the following inequality. So I'm going to leave that up. Leave that later. Oops. So this is equal to 2 to the L. I keep writing 4. Okay. So what we say is that I'm going to look at the set of descendant. Okay. So code word. So this code word over here has a length of 2. Okay. This code word has a length of 2, and it has descendants all the way down here. Okay. And the tree is of length 4, of height 4. So how many descendants would it have? Well, it's going to have basically 2 to the power 4 minus 2 descendants. It means 4 descendants. If I had a code word of height over here, for example, it would have 8 descendants, right? So if the code word is of length L sub I, then the number of descendants it corresponds to is 2 to the power L minus L sub I. Okay? Is that clear? It's just a simple mathematical fact. So we know that these descendant nodes over here, if you just look at those descendant nodes, which are these rectangles like so, these are non-overlapping. Just ignore all the others. Okay? If you just ignore everybody else and just look at the descendants, we can of course note that this has 0 descendants. So this corresponds to 2 to the power L minus L, which is equal to 1. So they just contribute 1. Okay, this is themselves, okay, into this. And so these circular ones are sort of the dummy space. It was not used by anybody, right? It's like those ones when I was coding from digit strings 0 to 9 using 4 bits. I had these 4 unused, I had everything 10 to 15 was unused, right? So that's 6 unused spaces. Those correspond to these circles over here. So we certainly know that these rectangles, which are orange rectangles or white rectangles, which correspond to this sigma I 2 to the L minus Li, where I'm summing over all possible code words, is going to be less than or equal to 2 to the L. Because all this is saying is that at most these orange and white rectangles span the entire leaf space, right? Which means at most you're going to have some all the circles go away, right? That's the worst you could do. You could never have anything that. So you have that inequality. And if you divide both sides by 2 to the L, we get 2 to the sigma 2 to the minus Li is less than or equal to 1. And this is the Kraft inequality. This one right here is called the Kraft inequality. It's named after the guy who proved it, which is Kraft. Okay? Any questions about this over here? Yeah.
You say descendants, only the terminal nodes.
Terminal nodes, correct. Leaf nodes that descend, not the tree, but just in the leaf nodes, correct. Yeah. Otherwise, we won't get 2 to the L minus Li. We'll get something 2 to the something L minus Li plus 1 or so. I don't know what it is. Yeah. Okay. So just by doing this counting of the leaves, we know that they're all going to be either white boxes or orange boxes or circles. If you ignore the circles, the sum of these two must be less than or equal to 2 to the L, and that's what this expresses, and then you just get this. So how do we interpret this? If I give you a code book, I know the lengths of the codes, right? L sub I. I just simply sum up this quantity, and if it's less than or equal to 1, then I know it's feasible. Okay, I don't know what it is. Okay, I don't necessarily even need to know what it is. I can tell you it's feasible. However, it's greater than 1, it's not feasible. Can't build a tree. Okay, so in the homework question, I gave you the L sub I. You were 2, 2, and 4. So we have basically 2 to the minus 2 plus 2 to the minus 2 plus 2 to the minus 4, which is 1 over 4 plus 1 over 4 plus 1 over 16. And this is less than or equal to 1. So this is certainly a feasible code, right? So Kraft inequality does not preclude this code. However, if I were to give you a code with lengths were 1, 1, and 4, that wouldn't work, because then you have 1 over, it's too much. Or actually, right, 1, 1, 4 wouldn't work. 2 to the minus 1 is 1 over 2, right? So this would be 1 over 2 plus 1 over 2 plus 1 over 16 is not less than or equal to 1. So this is an invalid code, and that's a valid code. It can certainly be done, okay? It's a valid instantaneous code. So the Kraft inequality is useful for one reason, because you can just take a look at the lengths of the codes, not even look at the codes, and simply say, that's not instantaneous. Okay? Out of the question, not going to work, right? We don't even need to construct the whole tree. Okay? It's a weak bound, but it's certainly useful to have. Any questions about this? Okay, so the nice thing about the Kraft inequality is that this Kraft inequality allows us to compute this one over here. So I'm going to do that computation, which is a simple minimization, and then we'll take a break after that. Okay, so in another few minutes we should be able to compute this value over here. Okay. Any questions about this so far? Okay. So let's look at the how to do the minimization for instantaneous codes. This is not for all codes. Okay. So we want to relate the minimum expected code word length to its message entropy. So far we haven't said anything about the message entropy. We know that this P sub pxi, okay, so we certainly know that sum over x, okay, pxi log base 2 pxi is going to be the h, the entropy of the message source, right? So if you know all the messages, the probability of that message, we certainly know that this is the message entropy, right? So we haven't said anything about entropy so far. What we're going to show now is this thing over here. For the optimal code, the expected code word length is in fact the message entropy itself of the source. So the message source entropy tells us exactly the shortest expected code word length. So if a message source has entropy of 24 bits, there is no instantaneous code which on average in expectation has a length less than 24 bits. Okay. So to prove that, what we do is that we first consider the value e, which I've already written over there as sum over I, pi. So I'm going to just write pxi else Li. So what did I put over there? I think that's what I said. So that's the value E, and I want to minimize this. Okay, subject to, now we have to do this subject to constraint, subject to sigma I 2 to the minus Li less than equal to 1. So that's the Kraft inequality. So we have this, but if it's instantaneous, it has to do this as well. So how many of you are familiar with Lagrangian optimization method of Lagrangian multipliers? 1, 2, 3. Okay. So whenever we have a function fx, we want to minimize or maximize fx subject to gx. Then what we do is we basically minimize fx plus lambda gx, okay, and and if you do that, we essentially have to compute the derivative of this fx plus lambda gx with respect to x and respect to lambda, okay, and we set those to 0, and then we compute the the minimizing value of lambda. So this is called the method of Lagrangian multipliers. That's called the Lagrange multiplier right there. And if you want to study more about it, if you look at the chapter on optimization online, you can see the section at the end on Lagrangian multipliers. The reason why it works is it's a fairly interesting argument why it works, but for now we're just going to say, okay, it works. So this is fx and this is gx. So what we really have to do is to set up this, it's called a Lagrange function, which is just a sum sigma I pxi li plus lambda sigma I 2 to the minus li. So that's my function g, and what I need to do then is, this actually is a function of all the L sub i's, okay, the variables actually L sub I, so you compute the partial derivatives of g with respect to L sub I, and for doing this I have to assume that the li's are reals. Actually li's are integers, okay, so I'm going to wave my hands and pretend they're reals, okay, because the partial derivatives are not defined for integers, right? We don't really have li plus delta li. We don't have that. We just have li. But it turns out that this kind of hack, it's a mathematical hack, does work, okay? And it can be shown for integers also the same, using a different approach it works. But just to get some intuition, we'll do this mathematical hack. If I take the partial derivative with respect to L sub I, I basically get, well, this is pxi li, so that's a constant with respect to li. That's just a constant. So that drops out, and all the derivatives of li with respect to lj, well, those are 0. They just drop out as well. So all you get is nothing more than pxi, okay? And then from here, we get lambda, and then the derivative of 2 to the minus x is going to be 2 to the minus x, and then ln 2. Okay, so because we're going to take the, that's the, so ln, well, I should call it log. Actually, no, it's ln 2 because, oops. Because we are taking e to the x, so the ln is log natural to base e, okay? So because the e to the x, the derivative of e to the x is e to the x, but the derivative of 2 to the x is 2 to the x ln 2, okay? That's what we do. So this is basically a constant e to the whatever the ratio, whatever 2 is in base e, you have to do that over there. And then if we just expand this, we're going to set this to equal to 0 to find the minimal point, and then we are going to get this to 0. We get 2 to the minus li equals p of xi over lambda ln 2. This is just setting this to 0, right? We're going to set the partial derivative to 0. That's what we do for Lagrangian multipliers. The second thing is that we're going to assume that the Kraft inequality is binding. By binding, when you do optimization, we mean that this is the constraint that matters, okay? In which binding case is when the inequality becomes the equality. So when it's binding, implies that sigma I 2 to the minus li equal to 1. And so this allows us to write so this, if this is going to be the case, then this over here means this summation goes over here, because 2 to the minus Li is this. Is going to be sigma p of xi over lambda ln2 equals to 1, which means lambda is going to be equal to sigma p of xi over 1 over ln2. Okay, so I just move lambda to the other side and I get sigma, because lambda is a constant, it drops to the summation, so I get this. But this p sigma of all the probabilities is just 1, right? Because all the probabilities, all the messages equal to 1, so this becomes lambda equals 1 over ln2. And if you substitute that into here, basically we get over here lambda ln2 is going to be just 1, right? So we then get p of xi, okay, equals 2 to the minus li. Okay, because lambda ln2 equals 1. Okay, I'll walk through this in just a moment once again. So then E, which is going to be this over here, sigma I pxi li, is going to be nothing more than this. Okay, I can take the log of this side, sorry. So log base 2 of p of xi equals minus li, so that E equals sigma I pxi li is going to be sigma I minus sigma I p of xi log base 2 of pi, which is equal to just h of x by definition. So let me just walk through this so that I can connect all the dots. So we start with E, which is the expected code word length. Okay, that's by definition the length multiplied by its probability, right? So that's straightforward. We're subjecting it to the Kraft inequality because that constrains us. The method of Lagrange multipliers tells us we should take the function f plus lambda times the constraint and minimize that. And we do that by taking the partial derivatives with respect to actually to all the L sub I and lambda, but we don't need lambda over here because we're going to take the partial derivative with respect to L sub I. And that, by setting it to 0, is going to tell us the minimal point, right? It's optimal point, could be maximum, minimum. In this case, it turns out to be the minimum point. And the partial derivative is this, and we set that to 0. By doing that, we immediately get 2 to the Li is going to be pxi over lambda ln2. I'm missing a negative sign somewhere. There's a minus over here. Okay, because it's 2 to the minus Li, so I get minus over there because of that. So that gives me, from here, I straight away get 2 to the minus Li is this. And by having the binding constraint on the Kraft inequality, I also know sigma 2 to the Li equals 1. And so if I know this, I can take 2 to the minus Li over here and substitute the right-hand side. I get this one over here. And then this allows me to compute lambda to be just 1 over ln2. Right? This is just simple substitution over here. When I do that, I get pxi, which is here, because this denominator goes away. Lambda ln2 is equal to 1. So this goes away. So pxi is 2 to the minus li. Take logarithms on both sides. Get log pxi equals minus li. Okay, because it's just the logs of both sides. So then E, which I wrote down over there, is pxi li is going to be pxi log pxi, log pi, because I'm just putting that over here, log of p of xi. Okay, and that is the message entropy of the source hx. So what are we saying over here? If we kind of unpack all this, we're saying that E is equal to hx when you have the optimal code, optimal instantaneous code. Okay, because that's the optimization, right? So if I give you a message source, I tell you what its entropy is, I can tell you also the minimum expected code word length for that, for an instantaneous code. Okay, no instantaneous code can possibly have expected code word length lower than the entropy of the source. So again, to go up one more level abstraction, that means that if I give you a set of messages and I compute the entropy of the message source, I cannot code it with the instantaneous code any better than its entropy. I just can't do any better than that. Okay, if it's not instantaneous, that's a different question, but I can't code it better than its minimum entropy. Okay, so we now see that the entropy of a source, which was sort of arbitrarily defined as P log P, sigma P log P, now has this very, very deep meaning, which is that I can't do any better than that for instantaneous code. Okay, so it's not just that's one reason why I use P log P, because it gives us this very nice intuitive meaning of this is the amount of entropy, I have to use so many bits. Okay, so the more entropy there is, the more code bits I need to get my work done. Okay, to say that. Okay, of course we ignored the integrality constraints, but it turns out this derivation works even with integer constraints as well. Do you have a question? Yeah. Okay. Okay, so everything I said over here is also in the text. I don't think I missed any steps. So if this is a bit confusing, you can go back and read it. You do need to understand the method of Lagrange multipliers, but all we're saying there is simply that you need to use the sum, and then you set the partial derivative with respect to the underlying variables. Okay, so on that cheery note, we'll talk about Huffman codes. So we've established that if you know the probability distribution, the probability mass function corresponding to a random variable, which corresponds to a message source, we know its entropy, and from the entropy we also know that we have a lower bound on the instantaneous code. So one question you could ask is, okay, we know this, what is that instantaneous code anyway, which has this optimal value, right? So we have two kinds of results in math, the existential results and the constructive results. Okay, the existential result says there exists something. We don't know what it is, but it exists. Okay, and the constructive one says this is how you build it. So the existential ones are nice, and the constructive ones are useful. Okay, so to give a case in point, in game theory, if you study game theory, they have this existential proof of a Nash equilibrium. So Nash proved there exists a Nash equilibrium under certain conditions, but it doesn't tell you what it is. But then we have constructive proofs that said this is how you do something. So in mechanism design, in game theory, we said this is how you construct a mechanism which has certain properties. In information theory, we have some existence proofs and we have some constructive proofs. The existence proofs are, one of these is inequality, the Kraft inequality, and you can view the result about entropy as being sort of a lower bound result. But there is existential proof given for coding. And we'll talk about that later, which says that if you have a noisy channel, okay, channel which has errors in it, then there exists some code which, say, there exists a code which is very close to what's called the Shannon limit. So I will talk about that a bit later, what that means. But it doesn't tell you what that code is. And in fact, it took almost 50 years for people to figure out what that actual code is. Okay, it's called the two actually codes that do it. But that was existential proof. Huffman coding is nice because it's almost optimal. Okay, so the Huffman code basically says that if you give me a message, if you give me x and you give me the probability mass function of x, then I will give you a almost optimal code. An almost optimal code says that the e value of this is going to be less than or equal to h plus 1. What is e? E is the expected coded message length. It's going to be no greater than 1 bit more than what the entropy is. So if you have an intrinsic entropy of 20 bits, then the expected code length will be less than 21 bits. You can prove that. So it's a nice constructive thing. H plus 1, for most practical purposes, is good enough. So this is achieved by what's called the Huffman code. Yeah?
But can the value of E be less than the entropy?
No.
So it will be in between entropy?
Yeah, that's right. Sorry, yeah, that always is going to be true, right? So it lies in this very tight range between h and h plus 1. Yeah. Again, for instantaneous codes, right? So how does it work? So I'm not going to prove to you that the method I'm going to show you is going to achieve this limit, but instead I'll just tell you how it's done. And this is what's called, typically in computer science, we call this a greedy method. how many of you have seen the term greedy method before? Okay, so most of you should have seen it by now. So greedy method basically says, let's just be greedy and pick the best cases or whatever. So to show the greedy method in action, let me just do the homework problem. And there we had the following random variables. So I gave these. So there are 4 messages: hello, how are you, okay, bye, goodbye. And I wanted to use messages rather than symbols to show you this works with messages. Okay, so it doesn't matter what the messages are. So message 1 has a probability of 0.25. Message 2 has a probability of 0.2. Message 3 has a probability of 0.4. Message 4 has a probability of 0.1. Message 5 has a probability of 0.05. Okay, so those are the message probabilities, and I want to find the optimal code. The optimal code would have an expected message length, which is E, which is given by P sub I times the code word length of exactly the message entropy, which you can compute as Pi log Pi. So there's some message entropy over here. You know how to do it. This is what you did last homework assignment. What Huffman says is that let's just do the following. We're going to take the codes. We're just going to write them in increasing order along the bottom, which is 0.05, 0.1, 0.2, 0.25, and 0.4. So I can write them in this way. And then I take the greedy solution, which is, did I miss something? Yeah, okay. So you take these two. The least probability ones should be the longest code words. So we're going to put them at the bottom of the tree. And so if we start with them, they're going to get longer. So we're going to put these two at the bottom of the tree. So I can give this 0 or 1, or I can give them 1 and 0. It doesn't really matter because the code word length is preserved. And the total probability mass here is 0.15. And now you look at this 0.15 and these remaining guys, and you say, which are the lowest two? So in this case, this and this are the lowest two. So I go like this. And this is now going to have mass of 0.35. Okay. And I'm saying, okay, now which two are the lowest two? Well, this is already used up. So it's 0.25 and 0.35, the lowest two. So I get another leaf like this, and this is going to have a weight of 0.6. And obviously now these two are the only two left. So we're going to go like this, and this is going to be 1. And so we can say 0, 1 following convention, 0, 1, 0, 1. And so the code now says the message with the weight 0.4, which is this, is going to have the code. So this is the code. Is going to have the code 1. Okay. The message which has the weight 0.25, which is this one over here, is going to be 0, 1, because that's the path we took, 0 and then 1. The message which is weight 0.2 is going to be 0, 0, 1, and then the 0.05 is going to be 0, 0, 0, 0, and this is going to be 0, 0, 0, 1. Okay. And you can check for yourself that it's instantaneous. And moreover, you'll find that the entropy of this, which you can compute, so the mean message length of this, which will be E, you'll compute is going to be H. You know H, you can compute H, and you'll find that E is going to be less than H plus 1. It will be between H and H plus 1. Okay, you can certainly try that out if you want. And so that's the Huffman code. Okay, so Huffman code is telling you that in expectation it is the optimal code, but doesn't mean always. And the reason is because I might have a message which is, for example, a particular message, maybe message 5 repeated 5 times. I could say the message 5, 5, 5, 5, 5. Okay, that could be, certainly it's a valid message. It's a very unlikely message because the probability of that message is what, this is only 5%. So it's very, very unlikely. For that message, the Huffman code is going to be quite long. Okay, so for specific message instances, the Huffman code would be longer than some other code. However, if this is the correct probability mass function, then in expectation, the Huffman code is going to be constructive and also going to have a value which is going to be so the mean message length is going to be bounded by H plus 1 bits. Okay, the mean message length is going to be bounded in expectation. Mean coded message length. Okay, are there any questions about this over here? Okay, yeah.
Like at 0.35 and 0.25.
Yeah.
shouldn't 0.25 be on the left?
It doesn't matter if it's left or right because, yeah. I mean, I just put this increasing order because then we just need to compare this and this to see whether I'm going to take these two or this one. Just makes it easier computationally. But the codes are equivalent because I could certainly swap, zeros and ones. I could put a 0 here and a 1 here, and that's also a Huffman code. So Huffman codes are not unique. Okay? So I could have done the same thing where I could have put over here 0 and made this a 1, and then I would rewrite the code book, but the message lengths don't change, right? Because all we care about are the positions on the tree rather than the actual values. So Huffman codes are definitely not unique. All right, so that's basically the last thing I want to talk about today. So next time we'll start with channels.